Good morning, good afternoon, good evening, wherever you might be, and welcome to a physics post on ice. Ice cold beauty. When ice cracks, it can make the surface of a lake sing. It sounds like the music of the cosmos, or like a quiet, high-frequency thunderstorm. In the blog post linked below, there's a nice video of a woman.
Have you ever heard this sound before?
Goes out.
It's my absolute favorite sound, and it's been fascinating me for many years now. But I had never heard about it before.
This woman goes out onto the ice and records the sounds it makes, and it makes these wonderful cosmic sounds. And I want to think about similarities between the cosmos and ice. Water has unique phase transitions compared to other molecules because it has a larger volume after it freezes, leading to the sorts of cracks that can be heard on the surface of a lake. In liquid form, the molecules pack together more tightly and form loops and strings, but in the frozen state, they form a crystalline lattice that comes in several different forms when it is frozen under high pressure. It comes in ice 1, 2, 3, 4, 5, etc. And if you've read Kurt Vonnegut's book, The Cat's Cradle, there is a deadly and imaginary ice 9, which freezes at room temperature and atmospheric pressure, following a seeded nucleation process. Thank goodness it doesn't exist. I will instead focus on regular old run-of-the-mill ice that freezes at 0 degrees Celsius, and I will explain why it is slippery and why it makes cosmic sounds when it cracks. The first thing to do when you want to know about how ice works is to picture a charge, an electric charge, as something real, not abstract, something that is defined by a swirling motion. It's a thing, and it's defined by circulation. Things that swirl in the same direction repel one another, and things that swirl in opposite directions will attract. This is something you can feel in your body when you do a little dance with your hands. The atoms in a piece of ice have a swirling motion that is in the same direction as the swirling motion in another solid, and that is why the two objects repel when they touch one another. It is why they are solid. When ice is touched, it has a swirling motion on one length scale, which is responsible for its solidity, and it has a swirling motion in the opposite direction on another length scale, which is responsible for its slipperiness. Picture the surface of the ice trying to mix itself together with the surface of your shoe as you walk, thereby creating a turbulent, swirling flow which is in the opposite direction of the swirling motion responsible for the solidity. In other words, the electrons or charges on the surface of ice are less strongly bound than the electrons within ice, and this allows them to move more freely so that they move relative to the electrons in your shoe. Electrons which move in the same direction repel, of course, but if they are moving in opposite directions, they attract. the motion of the surface electrons on ice relative to the electrons in your shoe is responsible for ice's slipperiness. Electrons in metal are also quite mobile, and that is why an ice skate slips more than your shoe does. It isn't particularly useful to describe ice's slipperiness in terms of wetness, dryness, or surface melting as is done in the YouTube video I found, because the friction coefficient of ice doesn't get worse when you drop the ambient temperature. So this YouTube video I found on why ice is slippery is just awful. He takes 10 minutes to say over and over again that ice is slippery because a thin layer of water melts in a complicated and abstract way. He then concludes that ice's slipperiness is still mysterious and still needs to be studied by the theoretical physics morons like him. I've explained in this article, I'm trying to explain in this video, why a mysterious and complex form of melting is a stupid way to explain ice's slipperiness, because there are other, more simple, geometric, intuitive ways to describe it in terms of electric charge and relative motion of things that circulate. If one insists, you could describe the motion of the surface electrons or molecules as a sort of friction melting, an abstract form of melting, but as was done by this guy in the YouTube video in a convoluted way. But I decide whether or not I like a language based on how useful it is. I think that one could make a better quantitative model by imagining electric current rather than by imagining an abstract form of melting. Then again, the physics tastemakers in the pop science community usually have very odd preferences in these aesthetic matters. I think they describe things in overly complicated ways because mystery is how you get people to give you money and how you get them to keep watching you, because if you do a bad job of explaining something, they'll often just keep listening to try and figure out what it is that you're saying with the belief that what you're saying is true and important, when a lot of times they're just full of it. Now back to ice. Ice and the cosmic sounds that the surface of an icy lake makes. These wonderful sounds that inspired this woman from Scandinavia to go out all by herself with audio equipment to record them. Why do they sound like softly rolling thunder or like the eerie noises picked up by space probes traveling through the solar system? Here's a video of NASA's space sounds. Is it going to start? There we go. The sounds you hear in space. I sure hope it's not a hoax. You know, today we have so little trust in all of our institutions. Do we trust that these sounds actually came from a probe in the middle of outer space, or that somebody just wanted us to think that they were? That would be so sad. I don't think that's the case. I trust people more than that. Maybe I shouldn't. Perhaps the reason that ice at the surface of an icy lake and the sounds that NASA records from outer space, that they sound similar because the vacuum of space is actually quite energy dense, and in a sense that makes it extremely hard, like ice, that it cracks and makes noises. But precisely how hard might the vacuum of space be? I mean, of course we go right through it, but it's energy dense, and yeah, it's hard to think about. But 100 years ago, physicists would have had a lot to say on the topic of how hard empty space is. But today, that's not really part of the conversation. If you look back at the still valid language of yesteryear, the hardness of space depends on how much it has been stretched or compressed by a gravitational or electric field. Oliver Heaviside thought that lightning and sparks were what happened when space stretched too far in one direction and became thin and weak in the other direction, allowing space to press in from two sides and cause a crack. In more technical language, he would talk about sparks and lightning in terms of the elasticity of a non-conducting material. Sometimes I like to picture two clouds holding the ends of a network of rubber bands. The greater the distance between the clouds is, the longer the rubber bands are and the more they can potentially stretch. As the electric potentials between the two clouds grow, the clouds pull harder on the ends of the rubber band until it snaps like a bolt of lightning. So with these two images, you can imagine them as two sides of the same coin. And one, you have a network of bands. That's one side of the mirror, and the other side of the mirror is a very hard substance that pushes in and cracks, and that the cracks are the points of stress are the rubber bands. It's possible to think about, but it might take you some visualization effort. In a book I have linked to in the blog post below, it's from 1920. It has a wonderful example of this very intuitive style of thinking on both sides of the mirror in terms of real physical things that produce the sparks and electrical effects that we see, but that are hard to explain without imagining that they're happening in a real physical medium. I'll now summarize some of the key concepts. Space can be described with the permeability and elastivity of space. Well, permeability and elastivity. That it's a substance with holes, permeability, and it's stretchy, it has elastivity. The permeability describes the ability of the substance to support the formation of a magnetic field, while the permittivity describes the ability to support the formation of an electric field. Elastivity is the inverse of the permittivity, and in free space, the permeability to permittivity ratio is 1, as in they are the same thing, which makes sense. Elastance is the inverse of capacitance, and it results from the elastivity of a material. It is one of a suite of terms coined by Oliver Heaviside back in the 1800s, where ants words correspond to measurable things in electric circuits, and ivity words are related to field descriptions, which are derived from measurable things. It's the abstraction, something you can imagine or model on a computer. The dielectric constant, or relative permittivity, measures the ability of a material to store electrical energy in an electric field. It is equal to the permittivity of a substance divided by the permittivity of free space. Hardness accounts for the strengths of chemical bonds, of which there are none in completely empty space. So that makes a question about how hard empty space is rather difficult to interpret unless we redefine hardness as the ability to sustain an electric and magnetic field in perfect balance. When they are out of balance, things tend to fall apart or get bent. The dielectric constant of a material tends to increase linearly with the hardness of a material. And since the dielectric constant of free space is 1, and negative dielectric materials do not occur without careful engineering, it is safe to say that space is the softest material around, which makes sense, but only when it is not getting stretched in the vicinity of electric or gravitational fields. When it is, for example, stretched, when free space is stretched by the presence of a heavy sun and bending starlight, its dielectric constant is certainly not acting like it is equal to 1. This space is acting rather viscous, and under even more extreme conditions, when lightning strikes, space cracks and acts extremely hard and brittle. In more relativistic, less absolute terms, if you see a flying javelin or a comet which is long enough to be bent by the gravitational field of a planet, then you are observing the effect of changes in the hardness of space. We could split hairs over what it means to see a javelin and whether the hardness of space changes or the hardness of a javelin changes as a result of changes in space-time, but that sort of hurts my brain today. I think that a description of which is true enough to our everyday physics is that the javelin gets bent due to varying hardness of the space around it, or around the planet. If you shot a small flexible arrow into the rind of a giant watermelon, I believe that it would lodge itself in the watermelon rind with a bent shape. However, I've never actually seen such an experiment performed. Instead, I see flashes of lightning and I hear rolls of thunder when space cracks in the sky, releasing echoing, rolling sounds that confuse gravitational wave detectors. I also see young women going out alone to record the quiet thunder coming from the surface of an icy lake. I see young men teaming up to record the quiet thunder from space probes, as they visit distant planets. And while I am sympathetic to these focused efforts, I'd rather write a poem. Clouds, ghostly muses born of Zeus's lightning, are thoughts condensing in our minds. Precipitated by Apollo's light, these immortals cast shadows that determine their future forms. In Plato's cave, we fear such shadows of ourselves, knowing their power to bewilder and ensnare. By Prometheus's firelight, we tell ghost stories to remind ourselves of things that can't be said. Physics is full of things that cannot be said, because they officially do not exist if you do not speak the correct language. A good example of a physics language that is so far out of fashion that it is practically taboo is that of the magnetic monopole. It has become a FNORD for any well-trained physicist. But why do I care about any of this? Why do people see beauty in any of these ideas? Why does anyone care? I think we invest in physics to distract ourselves from our most basic fears of our mortality as individuals and as a species. This is good when it is distributed widely in the form of wonder and curiosity, but when it assumes a concentrated form, as in big science laboratories funded by the government and fueled by fear, these laboratories that emerged as spin-offs of the terror-driven Manhattan Project, I think we allow our distraction to consume us and to consume the energy of our naive children who are taught that the transformation of a muon into an electron is an abstraction, and that it is nothing like a layer of ice breaking free from a frozen vortex flying through space. Set the children free from this abstraction. When people get too hard and pressurized, they crack. And I usually try to end each post, I'm trying to end each post with a song, but I don't really have one for this one, unless I can think of one. Ice. What's an ice song? I like this song. I wouldn't want to ruin this peaceful sound by singing over it. So, thank you for watching, and I hope you tune into my next post, and I hope you take a look at the novels I wrote. They really kind of came to me in a burst of inspiration, and that felt special, and the journey of writing them taught me some things. I think that other people would enjoy that experience too. So, until next time.